Hi, my name is Octavio Pardo. Thank you all for watching this presentation, and thanks to the ATypI for giving me the chance to present to you all today. I hate that we cannot do this in person, but I'm sure that we're not too far from meeting again, so stay strong. I'm here to explain you a little bit about the PhD project that I'm doing at the Royal Danish Academy of Architecture, Design and Conservation, which I'm in its final stages. It's centered around the legibility for low vision people. However, not completely satisfied with the conventional approach to legibility I saw in other research papers, I studied quite a lot to build a legibility framework, whereas a typographer I could feel much more comfortable. I'm going to try to give you a small hint of that work here. I call the presentation Legibility in Black and White because I believe that type designers should build their construction of legibility around a strong understanding of our psychophysical perception of negative and positive spaces, as I will try to explain in a moment. In my framework, I try to link intimate concepts of type design like rhythm and counter shapes inspired by fundamental texts like the stroke, for example, with a critical understanding of how our visual system works. Some of the things I'm going to explain can also be found in the fantastic lecture given by Kevin Larson at the ATypI in Sao Paulo, but I found completely necessary reviewing them again to make the presentation more understandable. If you haven't seen Kevin's talk, it's an absolute must. And now let's go. I guess many of you know what this is. This is called the Snellen chart, created in 1862 by the Deutsche ophthalmologist Hermann Snellen. And it's a test that I'm sure all of you have ever taken at least once. So this is a tool that ophthalmologists use to measure our visual acuity. But it doesn't use exactly letters, but something else called optotypes that work in a smart way related to the visual frequency concept that we will see in a second. But what you might not know is that in the last years, there is some consensus among the community of psychophysicists that the chart is not accurate enough to measure our general visual performance. And many scientists tend to prefer much more this other tool here. This graph, developed by the British researchers Campbell and Robson in 1968, was part of a large group of experiments to study our contrast sensitivity. As you can see, this artifact consists of a sinusoidal gradient that increases along the abscissa left to right in a spatial frequency and in contrast in the ordinate top to bottom. It might not look like it, but the bars go up to the top, and depending on your sensibility, you might see it or not. I'm about to explain some hardcore stuff, so I find it necessary to clarify first a couple of concepts. What you see here on the left is a visual representation of the transition of dark to light on the right. This is called a Fourier transform, named after the French mathematician Joseph Fourier. If you look at the graph on the left, when it hits the top in 1, it's represented by pitch dark on the right, and when you hit -1, you're in total clarity. As you can see, the transition is smooth and gradual, and so is the curve. This is called a sinusoidal wave. In contrast to this, the concept is the same, but the transition, instead of happening gradually, happens suddenly. This is what we call a square wave. When you have an oscillation like this, like the one here, is what we call a cycle. So this is one cycle, or one full variation of black to white, and then back to the same origin point. The second concept I want to talk about is visual angle. In psychophysics, we refer to visual angle as the approximate angle of elements projected in our retina. This angle is independent of the size of the relative distance of objects. So if these letters were three-dimensional and ask you which one is the biggest one or which one is placed the farthest one from us, we couldn't really know because A might be the smallest one, but it's just the closest to us, or C could be the largest and farthest from us. So that is why we prefer visual angle, or as I said, the angle of things projected in the retina. The maths to find out the visual angle is a bit more complicated than this, but this simplified formula works pretty well. You divide the target's physical size by the viewing distance, all in the same units, and then you multiply it per 57.3. Don't ask why. For example, 1 centimeter of Helvetic uppercase at an average reading distance of around 30 centimeters equals more or less to 1.81 degrees. And here's the amount of text that will fit in that 1.91 degrees or 1 centimeter. Below you can see that 1 degree equals to 21 points of Helvetica. Again, in a normal reading distance. And when you read a long text at that average reading distance, 1 degree equals more or less to 3 letters of Georgia at 12 points. Okay. However, as I said, at the moment that you alter the distance or the size, things change. So, for example, when you see text at 90 points at a distance of 10 centimeters, it looks the same as 1,800 points at 2 meters, which is around 18 degrees. I hope this makes sense. If you want to calculate the visual angle in relation to type, Nick Sherman and Chris Lewis have developed an awesome site called sizecalc.com that, of course, I use all the time. If we combine these two concepts, suddenly we have a way to measure our contrast sensitivity, which is cycles per degree. So our contrast sensitivity depends on our ability to detect cycles at different frequencies. We define the spatial frequency of a pattern as the number of cycles that occur in 1 degree of visual angle. So, for example, here in this image here, if the red square was 1 degree, this will be a 2 cycles per degree pattern, or 2 full variations of black to white. As spatial frequency increases, there will be more cycles per degree of visual angle, and the bars will become narrower and harder to perceive. If you think about it, this idea is intimately linked with our concept of resolution. When we can see the variations in contrast in a shape, we can resolve that shape. But when we can perceive those variations, we start perceiving things that are something else, different artifacts. Like this square made of lines that, when reduced beyond our threshold, it becomes a solid shape to our eyes. Let's see how this works applied to text. If we have one of the most simple letters we can have, lowercase I, our ability to perceive it will depend on our ability to discern the letter's subtleties against the background and between its parts. So in the image here, think of the red bars as the highest sensibility of your eyes, or in other words, if these bars were from the square made of bars from the previous slides, imagine it has the size right before we start perceiving it as a solid shape. So this eye is smaller than a cycle at your highest sensibility. Or in other words, the letter is placed either too far or is too small or at a minimal visual angle. So we simply cannot resolve that letter. I don't know if you can see it, but it's right there. On the other hand, if the letter is large enough or is close enough, or in other words, is in a visual angle comfortable to us, and the contrast with the background is sufficient, we can perceive the little nuisances and the little details of the letter and, of course, resolve it. This is a classic contrast sensitivity function graph. Here it shows that our highest sensibility is somewhere around 5 or 6 cycles per degree. It might seem a bit hard to understand here, but it's probably easier if we do this. Now you might start to get what's happening. Basically, everything that is out of this graph in terms of resolution of details and in contrast versus the background is more challenging for us to perceive, and those things inside are easier. Campbell and Robson's work was terrific, but I want to focus on one of the consequences of their findings that I consider of utmost importance for us as letter makers. The fact that a visual system processes low-frequency information and high-frequency information in different ways depending on the visual angle. This famous visual game explains this effect nicely. As you can see, this is an artifact that, when seen from up close, it shows a photo of Einstein, and from far it shows a photo of Marilyn. This happens because elements overlap at different visual frequencies, and our system has its own priorities on how to process it. So when we alter the visual angle at which we perceive the image by either making it smaller or moving it away, well, what's nice high frequencies go out of the graphic for us because we can't see them anymore. and what was too low, it becomes accessible. It might be easier in this video here. Okay, this was probably the heaviest part of the lecture. Now we're going to make it a bit lighter. One of the things you might have realized from the previous images is that everything we see has information at several levels. Things are not just low frequency when they are super close and high frequency when they are far away. Simply, we can only see the information when it's within a range of perception. It is true that in general, low frequencies tend to refer to the general aspect of what we see, while the high frequencies refer to extreme details. Let me show you how this idea of several levels of information work. Here we have the same eye as before. The whole block of the eye is simple and solid, so it's relatively easy to spot it. On the right, I have now the same eye, but I have introduced some high-frequency information. Do you see the little curvatures on the stem and in the dot? I call that high-frequency information because I cannot perceive those subtleties until they are not in the range where my high-frequency perception feels comfortable to resolve that shape. Here, check the example. The eyes are there, and I can detect them, but which one is which? I can't tell because I cannot see the high-frequency information to distinguish them. But once those subtleties are available to my perceptual system, I can see them, and then I can see, okay, yeah, I can distinguish that high-frequency information, okay? Check this image here. Majah and colleagues developed it in 2002, and it's an artifact that it's great to explain the underlying mechanisms of the phenomenon that I'm showing you here, which are the different visual channels of our visual system. You can see how, depending on the visual angle or the information available, you end up perceiving one letter or another of the image's three possible letters. But explaining this will take much more than the 20 minutes I have today, so we should move on. However, the reason why I'm showing you this is not only for this image, but because in this article, Majak and his colleagues generalized the findings of Campbell and Robson into letterforms by saying that the low frequency information is on the solid parts of the letters, while the high frequency is on the contours. Remember the slides that we just saw with the letter I, you know? In these images here, I have separated the high frequency information and the low frequency information artificially. On the low frequency image, we can guess the shape of the letters, but it's the information on the high frequency side that give us the most data about how really the shape of letters are. Nuisances that we can only sense on one side can be perfectly resolved on the other. However, if we look at the same images but vary in the visual angle, it happens something similar to what happened with the image of Merlin and Einstein. High frequency data, the contours of the characters get blurry, and suddenly our visual system can only process low frequency information efficiently. When we analyze type under this optic, and we compare the contribution of each one of the levels of information to the reading experience, we can understand the relative values of design details versus well-defined proportions. We can understand why typefaces with different design features but structurally similar have been scoring equal in speed of reading tests for more than a century. We can understand why high contrast fonts can be hard to read at text size, or why Courier always scores so well in low vision tests. Look how all the shapes stand after removing the high-frequency information. This has provoked that for many years, scientists have thought that monospace fonts had some kind of advantage because our eyes can predict the position of letters, instead of considering just the relation of black and white, much more relaxing for our visual system, or the value of a low contrast in a serif font. Does this mean that we only use low frequencies to read small size text and the high frequencies when reading the big display text? Well, of course not. Several papers prove that information at different frequencies contribute. We just use a different distribution of information depending on the reading context. It's a matter of understanding where the emphasis should be put in each case. Every once in a while, a new phone is advertised as a new and improved design for people with visual impairments. But many times, its creators focus on what I consider secondary features, coming up with just like new serifs, ink traps, or slanted shapes. New solutions are presented with extravagant design decisions or features that creators do not understand or cannot explain why they work, if they do. What about the features that most intimately relate with our visual system, the color proportions of the letters, like and the rhythm, or in its most basic level, the relation between black and white? Our letters are the product of many different factors, the evolution through different histories, invasions, cultural reforms. We can still see the trace of the tools employed to shape them many centuries ago, or the impact of the formal and the informal writing, until the computer has freed us from any imagined instrumental restriction. But what we consider the conventional is the culmination of similar shapes and proportions repeated millions of times, fixating archetypes in the universal subconscious. But is the conventional similar to the legible? What is the difference? The conventional is related to how we understand type and our expectations about it, but not how we perceive it. We know there are some structural differences between how we understand letters and how we perceive them, as we know that since the early days of printing, punch cutters have been making optical adjustments to different type sizes. Now let's turn our attention to low vision people. If you believe what I just told you about how our visual system works, how do we understand letters in terms of visual frequencies and visual channels, and that perception and identification are not directly related, then this next question shouldn't be a shock. What happens when your visual system is different? What happens when you cannot see efficiently? We know of many different visual issues that we all can suffer, altering our regular visual perception and contrast sensitivity, and forcing people to use different reading strategies. For example, hypermetropy, or cataracts in older people that alter our capacity to perceive high visual frequencies efficiently. Or macular degeneration that creates a large field of impairment in the center field of the fovea and forces those who suffer it to read with what we call the parafoveal area. This area here. Visual perception is very different there, as the effect known as crowding gets really intense and annoying. What are the optimal configurations for them? But most important, how do we find them? My PhD is my attempt to answer this question. Let me introduce you to ecadonc ears. It's named that way after the old Greek monsters of 100 arms and 50 faces. Ecadonc ears is a lowercase variable font constructed following the same ideas David Berlow used for his enormous Amstelvar. Instead of varying along the axis of weight, width, or contrast, it isolates black and white dimensions horizontally and vertically. In that way, we can configure ecadonc ears in many different shapes while obtaining parametric constructive information of the current instance in use. We can explore wider or narrower configurations while keeping the white space equal or anything you can think of. This exploration is done using a Bayesian algorithm and can be applied to any kind of experiments like a lexical decision task or a letter acuity. And as we always do at the research department of the Royal Danish Academy, the exploration is based on performance of the instances and not on personal preferences or qualitative data. Let me quickly explain to you how do Bayesian algorithms work. Imagine an axis of variation like this. You could randomly try instances every 10 or 5 steps and gather data on each of them. Eventually, you will have explored the whole axis. However, this has the inconvenience that it's exceptionally dull and inefficient, and it makes experimental times too long. Bayesian algorithms are sort of a basic learning algorithm that mixes random explorations with database decisions. In that way, we can optimize experimental time and consider other factors like interactions between different variables. As you can see, this approach is a mix of the most basic typographic understanding with some cutting-edge tools. One of the most interesting advantages is that we can easily customize the framework for any legibility scenario, And as it's based on a psychophysical understanding of legibility, the information can also be exported and reused for different scripts or contexts. This project's primary goal is not to create a font prepared to help the low vision community, but gather structural parametric information so all of you can build fonts in the future prepared to help them. I like to think that my research does not finish with my own font, but it will hopefully continue in yours. And that was it. I will have loved to tell you many more things, but my time is over. This project is in current development, and we expect it will conclude. We will conclude in the next year. I will keep you updated about the results. Yeah, thanks for listening, and please take great care. Bye.
Ask.
Can you hear me?
Yes.
Good. Excellent.
So we have a question from Felix. Is there an automated way to split low frequency information from high frequency information?
No,
For example,
no.
Eclipse plugin.
Yep. No. Actually, what I did was quite abstract and artificial. Okay, obviously your visual system works. It's a bit more complex than that. We need to consider different contrast with the background and so on. Okay, scientists sometimes use and software that I can't remember of. Can look for it, but no, you can't do that in Eclipse. No.
So Siva asks, is that what Gaussian blur does?
The principle is more or less similar. Okay, what you need to understand when it comes to high. So this took me a lot to understand it and process it while I was studying it. But basically, what you need to understand is that the difference between high frequency information and low frequency information, it's a distribution of the information space. Okay, so for example, if you have like a square, it means like all your information is contained here. If you blur it, it means that you disperse the information, and that's what we call, that's the low frequency, because suddenly, boom, you're dispersing information. So the principle is is very similar. I don't know the principles between Gaussian blur, but at least the result looks very similar.
Okay, thank you very much. Is there any more questions to ask? If not, also there is Hangout session where we can also.
Good. I hope I didn't kill you.
Okay, so Eva, we have another question. In your conclusion, is the inner white space more important than the letter form?
No, it's both. It's both the positive and the negative. Okay, one of the things I didn't do in the talk that I should have done, and I thought of it afterwards, is that when you think about the letter I, the example is fine. But if you think about, for example, a letter with a counter shape like N, suddenly you in N, this idea of the positive and negative space, and then the value of the negative space to perceive not only the contours but also the inside makes more sense. So think, for example, okay, I don't know if you know a font like Climax or Mysutura that have counters extremely similar, extremely reduced. Okay, so if you think of those letters, for example, and you see them from the distance, you're going to perceive them like a whole block. So it's true that you need that counter to be big enough so they stop looking like a block, and then you start perceiving, okay, it's an N because I can see the counter. Okay, but then the counter only is not enough, because if the letter is too light, it's going to disappear from your eyes. Okay, so it's about this balance, and the point is that we've been reading for 5-6 centuries like these archetypes, so we're extremely used to see this idea of proportion of 5:1, for example, in terms of black and white. But the point is that we've been reading with our phobia, with our area of maximum perception. So the thing I'm looking for in this PhD is try to find, okay, is there actually, will we benefit from different configurations when we read, in the parafoveal area, or when we read with the specific visual conditions that alter our regular perception?